We all use electricity, right? I mean, it's just there, lights, phones, everything.
Yeah, it's become so fundamental that we hardly ever stop to think about it.
Exactly. But behind the scenes, well, there's this whole world of making sure it all runs smoothly and efficiently. And today we're diving into a topic called power factor correction, or PFC for short.
PFC, yeah.
Basically, it's a way to make those electrical systems work smarter, like less waste, potentially even saving some money.
Absolutely. It's one of those things, power factor correction, that even though it might seem kind of technical, it has a big impact. Huge impact, really, on how we power everything around us.
Right, and we're going to break it all down, like what exactly is power factor? Why does it matter so much? And all the different ways it can be, well, I guess you could say good or bad, right? Leading, lagging, unity.
Yeah, all of that.
And of course, the big question, how do we actually fix it when it's not ideal?
Yeah, the correction part, that's key.
Now, if you're hearing words like reactive power and kind of scratching your head, don't worry. We're going to make it all crystal clear. We're all about clear explanations, lots of analogies and those haha moments.
Definitely.
And we've got a brilliant electrical engineer with us today to guide us through this fascinating world. So welcome to the deep dive.
Glad to be here.
So we dug into some really interesting stuff for this deep dive, right? We've got articles from Schneider Electric. They really lay out why PFC is so important in these, modern electrical systems we have.
Right.
And then there's these great videos, the engineering mindset, Musa Simple projects. They use these clever visuals and examples to show us how to actually calculate power factor and even correct it in real world situations.
Yeah, those are great resources. It's good to have that mix of like the theory and the hands-on stuff.
Totally. And our mission is simple, really. We want to give you, our listener, a clear understanding of what power factor correction is and why it's a big deal. No jargon, just straightforward explanations.
Right to the point.
So let's get started. What exactly is power factor? Like if you had to explain it simply.
Okay, so power factor, PF for short, it basically tells you how effectively you're using electrical power in a circuit, in an AC circuit to be specific. And it's a number, a ratio actually.
A ratio? Okay.
Yeah, so it's the true power, which we measure in kilowatts, kilowatt, divided by the apparent power, which is measured in kilovolt amperes, kVA.
Kilowatts, kilovolt ampere. So we're already getting a bit technical. Any chance for one of those analogies to make it click?
Oh, absolutely. The engineering mindset video, they use a great one, the beer analogy.
Okay, I'm intrigued.
So imagine you have a glass of beer. The actual beer itself, the liquid you drink, that's the true power, the kilowatt. That's what's actually doing the work, quenching your thirst.
Got it. The good stuff.
Right. Now, on top of that beer, you've got the foam.
Ah, yes, the foam.
That represents the reactive power, measured in kVAR. This power, it's necessary for some things, like creating magnetic fields in motors, but it doesn't directly contribute to the work being done. You can't drink the foam like you drink the beer.
Okay, I'm seeing it now. So the whole glass, beer, and foam together, that's the apparent power, the kVA. It's what the system seems to be using, and it's what you pay for.
Exactly. So power factor, it's like the ratio of the beer to the whole glass. High power factor, lots of beer, not much foam. Good value for your money. Low power factor, more foam, less beer. Not so efficient.
More beer, less foam. I think I'm starting to get this. So we want that beer, obviously. Now, you mentioned different types of power factor. What are those exactly?
Well, there's three main ones we talk about. Lagging power factor, leading power factor, and then there's unity power factor.
Lagging power factor. So something's lagging behind, I guess.
Right. In a lagging power factor, the current in the AC circuit, it lags behind the voltage. This happens a lot in systems with things called inductive loads.
Inductive loads, okay.
Like electric motors, transformers, anything that uses coils to create magnetic fields. That magnetic field actually causes a kind of delay in the current, so it peaks after the voltage.
So it's like the magnetic field is holding the current back a bit.
Yeah, you could say that.
And in these cases, the power factor is usually between 0 and 1, right?
Yeah, exactly. And there's this thing called the phase angle that's negative, but a lot of times we just talk about the absolute value of the power factor.
Got it. So in our beer analogy, the beer, the useful current, it's arriving late to the party because the magnetic field is slowing it down.
I like that. That's a good way to picture it.
So what about leading power factor then? Is that the opposite?
It is. In a leading power factor, the current actually leads the voltage. It peaks before the voltage. This happens in circuits with a lot of capacitors.
Capacitors. Okay, so lagging is more about motors and transformer. Leading is more about capacitors.
Yeah, generally. Although those inductive loads, the motors and transformers, they're way more common in most real-world situations.
Makes sense. So leading power factor, the phase angle is positive there, and the power factor is between -1 and 0, right?
Technically, yes. But again, we usually focus on the absolute value.
Okay, so we've got lagging, leading, and then there's unity power factor. That sounds like the best one.
It is. Unity power factor means the current and voltage are perfectly in sync. In phase, No reactive power, it's all doing useful work. Power factor is 1.
So that's like our perfect glass of pure beer, no foam, maximum efficiency.
Exactly. Pure efficiency.
All right, so we know what power factor is and the different types. But why does it actually matter? Why do we need to correct it when it's not ideal?
There are a lot of reasons, actually.
Yeah, Schneider Electric, they listed 5 key reasons.
Oh, yeah. 5, that's right.
Let's go through those. So the first one was reduce carbon footprint. How does improving power factor help the environment?
Well, when you have a low power factor, your system has to draw more current to do the same amount of work. It's like you're being less efficient.
Okay, so you're using more energy than you really need to.
Right. And with power factor correction, what you're doing is you're supplying that reactive power closer to where it's needed.
So you don't need as much current flowing through the whole system.
Exactly. Less current means less energy lost in transmission lines, and you don't need to generate as much power in the first place. And since a lot of power generation still uses fossil fuels...
That means fewer emissions, right?
Yeah, lower carbon footprint. It's about making the whole grid work smarter, not harder.
So it's better for the environment, it's more efficient. Okay, what about the second reason, increased load capacity? What's that about?
Think back to the beer analogy.
Okay, beer, I'm with you.
If you have a lot of foam, your glass is bigger than the actual beer you can drink. Same with electrical systems. When you have a lot of reactive power, the capacity of your system in kVA, it's bigger than the actual useful power in kilobody.
So by getting rid of that reactive power, you're basically freeing up space, right?
Exactly. You can connect more things, run more equipment without overloading the system. So if a business wants to expand, they might not need to upgrade their whole electrical supply, which can be expensive.
Less phone, more beer in the same glass. Love it. Okay, third reason, avoidance of penalties. I hear utility companies don't like low power factors. True.
Very true. Especially for big customers like factories or businesses that use a lot of power.
Right.
They often have these extra charges if your power factor is too low, usually below 0.95. But if you fix it, bring that power factor up, you can avoid those extra fees. It can save you a lot of money.
So it's a financial incentive to be efficient, basically. Makes sense. What about the fourth one? Enhance voltage stability. How does power factor affect voltage?
Low power factor means you need more current flowing through the system. And when current travels through wires, it loses some voltage along the way. It's like friction.
Okay, I get it. So more current, more voltage drop.
Right. And that can be bad for equipment. Motors might run less efficiently. Sensitive electronics could even get damaged. But by correcting power factor, you reduce the current so the voltage stays more stable. Everything runs better.
Keeps things smooth. And finally, the last reason, reduced maximum availability requirement. What does that even mean?
Well, it's about peak demand. When your power factor is low, your system might need a lot of power for a short period of time. It's like a sudden surge.
Okay, so it stresses the system more.
Right. But if you correct the power factor, you smooth out those peaks. Less stress on the power grid, less chance of outages.
Makes sense. So to sum it all up, fixing power factor, it's not just some technical detail. It saves money, it's better for the environment, it makes systems more reliable. It's really important. Now, the big question, what actually causes a bad power factor in the first place?
Most of the time, it's those inductive loads we talked about earlier. Motors, transformers, anything with coils. They create those magnetic fields, and those fields cause the current to lag behind the voltage. That's what gives you a lagging power factor.
Right, those pesky magnetic fields. And while capacitors can cause a leading power factor, it's much less common, right?
Yeah, the lagging power factor is definitely the more common issue.
All right, so now that we know the villain of the story, how do we fight back? How do we fix a bad power factor?
Well, the most common way to fix a lagging power factor is to add capacitors to the circuit.
Capacitors, interesting.
They basically do the opposite of inductors. They make the current lead the voltage. So you add capacitors to a circuit with inductive loads, and it kind of balances things out. Brings the current and voltage back in sync, improves the power factor.
Like a counterbalance.
Exactly. And if you had a leading power factor, you could theoretically use inductors to fix it, but that's pretty rare.
Got it. Now, in one of the videos, they had this little kit with a bunch of capacitors and switches. What was that all about?
That was probably showing what we call a capacitor bank.
Capacitor bank, okay.
Yeah, in factories and big buildings, you often have these banks of capacitors, and they can be switched in and out of the circuit as needed, depending on how much correction you need at any given time.
So it's like a toolbox of capacitors.
Exactly. And that little kit you saw, it probably let you manually switch different capacitors in and out to see how it affected the power factor, like a hands-on demonstration.
Pretty cool. So we add these capacitor banks, but are there different ways to actually implement them?
Yeah, there are. You can have fixed compensations where the capacitor bank is just permanently connected. This works well for loads that are pretty consistent.
Okay, fixed.
Then there's automatic compensation. This is more sophisticated. It uses a controller to automatically switch different capacitors in and out as the load changes. So it keeps the power factor optimized all the time.
So it adjusts on the fly. Makes sense.
And then there's dynamic compensation. That's for really big loads that change very quickly. It's more complex, often using specialized electronic devices.
So different tools for different jobs.
Right. You got to choose the right tool for the job.
Now, I know there's some math involved in figuring out exactly how much correction you need, right? Like what size capacitor bank.
Yeah, there is. But we can talk about it without getting too deep into the weeds.
Please, no deep weeds.
No problem. The basic idea is to calculate how much reactive power the capacitor bank needs to supply to reach your target power factor.
Okay, so we need to know our target.
Right. And there's this formula, QC equals P, tan feet. It looks complicated, but it's not that bad once you break it down.
All right, let's break it down.
So QC, that's the reactive power we need from the capacitor bank, measured in kVAR. P is the true power, the kW, our beer, from the analogy.
Okay, I remember the beer. What about those tanfus and tanfeth things?
So feet, that's the Greek letter phi. It represents the initial phase angle, like before you do any correction. And feet, that's phi prime. It's the phase angle you want to achieve after correction.
Okay, initial and target.
And the tangent of those angles, the tan F part, that's related to the ratio of reactive power to true power. So the whole formula is basically telling you the difference in reactive power you need to shift from your starting point to your goal.
Makes sense. But where do you even get those initial and target power factor values?
Sometimes you can find the initial power factor on your electricity bill, especially for businesses.
Oh, right.
Or you can measure it directly with special equipment. And the target power factor, that's something you decide based on how much you want to improve. Usually you aim for around 0.95 or higher.
To avoid those penalties and be efficient.
Exactly.
Now, in that engineering mindset video, they had an example calculation. 50 kilowatt a load, initial power factor of 0.78. They wanted to correct it to 0.96, and they needed a 25.5 kiloVAR capacitor. How did they get that number?
So they started with that 50 kilowatt a load and the 0.78 power factor. That means the apparent power, the kVA, was higher than the true power. They used the formula kVA equals kWPF and got about 64.1 kiloVA.
So the glass was bigger than the beer.
Right? Now remember, the lower the power factor, the bigger the phase angle, which means more reactive power, more foam.
So a lot of foam in this case.
Yeah, about 40.1 kiloVAR. Now they wanted to improve the power factor to 0.96. So with that same 50 kilowatts of true power, they needed an apparent power of about 52.1 kiloVA.
So a smaller glass.
Exactly. And that means the target reactive power would be much lower, only about 14.6 kiloVAR.
Okay, so less foam. But how does that tell us the size of the capacitor?
Well, the capacitor has to provide the difference between the initial and the target reactive power. So 40.1 kiloVAR minus 14.6 kiloVAR, that's about 25.5 kiloVAR. So they need a capacitor bank that can provide 25.5 kiloVAR.
Oh, I see. It fills the gap.
Exactly. It fills the reactive power gap.
That makes sense. So we've talked a lot about the technical stuff, but why is this especially important for businesses and factories as opposed to, regular homes?
Well, residential electricity bills usually only charge you for the real energy you use, the kilowatt hours. They don't really care about reactive power, the foam.
So my home phone is free.
Pretty much, yeah.
Nice, but for businesses, it's a different story.
Right. For big energy users, utility companies often charge extra for reactive power if your power factor is too low.
It's like a penalty for being inefficient.
Exactly. And there are good reasons for it. A low power factor for a big factory, it can strain the whole grid. More current flowing through wires, potential for voltage drops.
And those voltage drops, they can cause problems, right?
Absolutely. Equipment can malfunction, things can overheat.
Not good. So businesses have a real incentive to keep their power factor in check.
Yeah, both financially and for the sake of their equipment and the grid as a whole.
Now, speaking of real-world examples, that video from Musa Simple Projects, they showed a DIY capacitor bank, and they ran into a bit of trouble with something called inrush current. What's that all about?
Yes, inrush current. It's a common issue when you first connect a capacitor to a power source.
So like when you turn it on for the first time?
Yeah. Basically, the capacitor acts like a short circuit for a very short time. It draws a huge amount of current, much more than it normally would.
And that's bad.
It can be. It can damage switches, fuses, even the capacitor itself. In that video, the guy actually blew a switch because of inrush current. It shows how important this is.
Yikes. So what can you do about it?
Well, he mentioned a few things. You can use heavy-duty switches that can handle those surges. You can add resistors to slow down the charging process. Or you can use more advanced electronics that switch the capacitor on at just the right moment, when the voltage is zero.
So it's like a soft start for the capacitor. Clever.
Yeah, it's all about controlling that initial surge of current.
Now, I wanted to mention someone we came across in our research, Rafaعي. He's doing some really great work in making electrical engineering easier to understand.
Oh yeah, I've heard of him. He's got that calculator for power factor correction, right?
He does. It's a really handy tool for anyone who wants to actually put this stuff into practice.
Yeah, having tools like that can really bridge the gap between theory and application and makes it much more accessible.
Absolutely. And he also has this online platform, the Electrical and Energy Academy, or NIA Khanrabat Wattaka in Arabic, which is full of courses and resources. It's amazing what he's doing to make this knowledge available to more people.
It's really important work. The more people understand these concepts, the better we can design and operate our electrical systems.
I totally agree. So to wrap things up, we've covered a lot of ground today. We talked about what power factor is, why it matters, all the different types, the causes of poor power factor, and how to fix it. We even touched on some practical challenges and highlighted the work of people like Rafai who are making this knowledge more accessible. What are some key takeaways for our listeners?
Well, I think the main thing is to remember that power factor is all about efficiency. A low power factor means you're wasting energy, you're spending more money than you need to, and you're putting stress on the electrical grid. But the good news is it's fixable. By adding capacitors, you can improve your power factor, save money, and make your electrical system run smoother and more reliably.
And even if you're not an electrical engineer, understanding these basic concepts can really empower you to make smarter decisions about how you use energy. Especially for businesses, it can have a real impact on your bottom line.
And it's fascinating to think about the future of all this. As we rely more and more on electrical devices, how can we use technology to optimize power factor on a larger scale, maybe even at the level of individual appliances? It's a challenge, but it's also an exciting opportunity.
Absolutely. So for those of you who want to learn more, we definitely recommend checking out Rafai's resources. We'll be sure to include links in the show notes.
And thank you for having me on the show. It's been great talking about this stuff.
Thank you for sharing your expertise. And to all our listeners, thank you for joining us on the Deep Dive. We'll be back soon with another fascinating topic. Until then, keep those power factors high.